Hello, everybody. Thank you for coming to my virtual session. I'm Laurie Voss, VP of Developer Relations at LlamaIndex. In a former life, I co-founded NPM Inc. So some of you may know me from when I used to talk incessantly about JavaScript. Now I talk incessantly about AI, but the common thread is that I talk incessantly. Today, I'm going to be talking about LlamaIndex, starting with what it is. And then we're going to talk about agents and what they are, and how they work, and how to build one, including a multi-agent system. We're also going to talk about RAG, the most powerful tool that your agents can have to work with data. So what is LlamaIndex? It's a bunch of things. Start with the most obvious. We are a framework in both Python and TypeScript that helps you build generative AI applications. Today, we're going to be showing examples in Python, but our frameworks aren't all that we do at LlamaIndex. LlamaParse is a service from LlamaIndex that will parse complicated documents in any format into a form that can be understood by an LLM. This turns out to be critical for a lot of LLM applications, because if an LLM can't understand what it's reading, you get nonsense results. LlamaParse is free to use for 10,000 pages a month, and it will demonstrably improve what your app can do. Then there's Llama Cloud, which is our enterprise service. If what you want to do is connect your data source at one end and run retrieval augmented generation on the other end without having to think about all the stuff in the middle, then this is the service for you. Unlike the rest of LlamaIndex, it costs money. It is available as a SaaS at cloud.llamaindex.ai, or you can get it deployed to your own private cloud. And then there's Llama Hub, which is our registry of helper software. If you need to connect to any database in the world, we can do that. If you need to get your data out of Notion or Slack or Salesforce or YouTube, no problem. If you need to store your data in a vector store, we support all of them. And if you want to use OpenAI or Anthropic or DeepSeek or some other LLM, we support over 400 different LLMs, including local ones like Llama 3. And finally, if you want to build an agent and you want some pre-built tools to give to your agent, we have dozens of agent tools already built for you. But a really good question to ask is, why should you use LlamaIndex? In fact, why should you use any framework at all? And the answer is because we will help you go faster. You are a developer, you have limited time, you have actual business and technology problems to solve. You don't want to get stuck figuring out the basics. So with a framework, you get to skip the boilerplate, you get to avoid early pitfalls, you get a bunch of best practices for free, and you get to production faster. So what can you build in LlamaIndex? Well, anything you want to, obviously. But there are two things that we are particularly good at. One is AI agents, and the other is retrieval augmented generation. These two work really well together, and I'll be covering how to do both today. Before we talk about the how, though, it's worth covering why you should want to build these things. And before I do that, I should define what an agent is, because it's a term dramatically overused in the industry to the point of being meaningless. What I mean when I use it is semi-autonomous software. You give it a goal and a set of tools, and it will use an LLM to decide how to achieve that goal and what to do with those tools. Those tools can do anything. So they can retrieve information about the world, or they can take actions on behalf of the agent. Agents are a dramatic departure from traditional programming, where you define exactly what's going to happen in what order. In an agent, LLMs are given decision-making power. So they decide what tools to use, what order to use them in, what arguments to pass to those tools. And they are extremely flexible and powerful. They are good at dealing with the unexpected. So why build an agent? Usually when you have messy, unstructured data and you are trying to do something useful with it. LLMs are extremely good at handling messy inputs, and the world is full of messy inputs. So agents have a lot of applications. In general, I regard a good agent use case as any situation where an LLM is required to take a huge body of text or images and turn it into less text. So reading emails, handling customer service conversations, interpreting contracts, processing invoices, applying regulations, summarizing documents. These are all great use cases because you have a huge body of text and you need to turn it into something smaller, a calendar event, a decision, a report, or an answer to your question. The most obvious application of LLMs is a chat interface where you give it questions and it responds with answers, but I encourage you strongly to think beyond the chatbot model. LLMs are capable of taking unstructured data and turning it into structured data like JSON, which can then be passed to regular software, making that regular software suddenly capable of handling complex, messy, real-world inputs that it couldn't do before. LLMs under the hood in this way is a huge application surface, much bigger than the market for pure chatbots. You'll notice that I've talked a lot about what LLMs can do with unstructured data. LLMs are trained on mountains of public data, but unless you are building something extremely generic, you're going to want them to act on specific data. You're going to want them to act on your data. And they don't have your data. So you have to feed the LLM your data. Excuse me. The problem is that you have tons of data. You probably have tens of millions of tokens worth of data in your organization, and even the best LLM only accepts about 1 million tokens worth of data at a time. And even if you have less than 1 million tokens worth of data, LLMs charge you by the token. So you don't want to pass them all of your data indiscriminately every single time you have a question. The solution is retrieval augmented generation, or RAG, which allows you to be selective about what data you give to your LLM. By now, you're probably familiar with RAG, so I'm just going to do a very lightning quick refresher. The way RAG works is you take all of your data and you pass it through a technology related to LLMs called an embedding model. This converts your strings of data into arrays of numbers called vectors. These vectors represent the meaning of that data. The total set of possible vectors is known as vector space. So what you're doing is known as embedding them in vector space, or embeddings for short. Then when you get a query about your data, you pass your query through the same embedding model. And through the magic of semantic encoding, your query ends up mathematically nearby in vector space to the answer to that query, or rather to the data most relevant to answer that question. So you retrieve that relevant data and you pass it to your query, pass it and your query to the LLM, and it generates an answer, hence retrieval augmented generation. So agents can use RAG as one of their tools to access mountains of private real-time data that far exceeds what their training data covered. So agents need RAG, but RAG also needs agents. Agents are capable of introspection. Could this complicated question be a set of simpler questions? Did I just give a sensible answer to that question you asked me? Do I need to try extracting that data again? These are the sorts of questions that an agent can answer that RAG by itself does not handle. Agents can handle error correction. They can handle the unexpected in a way that RAG by itself cannot. In December of last year, Anthropic did an excellent post about how to build agents. It drew on their experience of building agents, and it formalized 5 core patterns that we recognized easily from our own work with agents. Those were chaining, routing, parallelization, orchestrator-workers, and evaluator-optimizers. One of the things I'm going to be doing today is showing you how to implement those agentic patterns in LlamaIndex to achieve fully capable agents. The first and most obvious pattern is the chain. You use an LLM to do some work, and you pass the output to another LLM, and so on to complete a complex task. That's trivial to build, especially in LlamaIndex. The building block of agentic programming in LlamaIndex is the workflow. It is a flexible event-based pattern that you can see here. Workflows are a series of steps connected by events, and you use the step decorator to define a step. You can use type annotations to indicate which events should trigger your step and what type of events it emits. LlamaIndex workflows have a built-in visualizer, the output of which you can see here. This is obviously a chain. You use the events, which are in green, to pass data from step to step, which are marked in blue, and then you return the result with a stop event. But there's much, much more to LLM applications than the chain. The next pattern that Anthropic called out is routing. In this one, you create several LLM-based tools to solve a problem in various ways, or to solve various different problems. And you give an initial LLM the choice of which tool to use. Again, this is not that complicated a concept, and it's simple to build in LlamaIndex. In workflows, you do this using branches. Instead of returning a single type of event, you can define your step as returning multiple possible types of events, and you can use logic from the LLM to determine which event type to return. This allows you to create branches, which can then in turn have their own chains as visualized here. From now on, I'm going to be sparing you the Python code. The next pattern is parallelization, which is where things get more interesting. Anthropic defines this as running several LLMs in parallel and aggregating their results. They define parallelization as having two flavors. The first flavor is sectioning. This is where you take the same input and act on it in completely different ways. An excellent example is guardrails. In one track, you can take a user's question and attempt to answer it. In a separate track, you can ask the LLM to scrutinize the question to see if the question is asking for something illegal or unethical or just dangerous. This allows you to take the output of the guardrails track and preempt the output or cancel work before you accidentally give your user a dangerous or illegal answer. The other flavor of parallelization is voting. This is where you give the same task to multiple different LLMs, or you give the same task in different ways to the same LLM, and you ask and you see if they all come up with the same answer. You can then take a unanimous or majority vote, and you can reduce errors and hallucinations this way. Hallucinations are a big problem when working with LLMs, so getting multiple chances to get the same answer significantly reduces your chance of your answer being hallucinated. Whichever flavor you use, parallelization is implemented the same way. LlamaIndex allows you to do this by emitting multiple events simultaneously. This will trigger multiple steps to execute concurrently. And we then have a utility function called collect events, which will aggregate the resulting responses and now allow another LLM to act upon them. And of course, your parallel calls can have their own chains and their own branches. You can see how things begin to get complex and why it's great to have a visualizer. The next pattern is orchestrator-workers. You can use an LLM to look at a complex task like a multi-part question and split it into several simpler questions, and then ask each of those questions in parallel. This is particularly valuable with RAG because RAG is only good at answering simple factual questions. It has trouble with complex or multi-part questions. You can then collect all of the answers and get another LLM to synthesize a single response that answers the full question. In LlamaIndex, this is implemented pretty much the same way as you implement parallelization. You just process the collected output differently. You can obviously combine all of these patterns in LlamaIndex, and in LlamaIndex we do. One of our favorite combinations is a multi-agent workflow, which we're going to see later. The final pattern that Anthropic called out is the evaluator-optimizer, which is also called self-reflection. In this pattern, you can use the LLM to decide whether the LLM has done a good job, and you can give it a chance to try again, optionally with feedback that might help it do better. This is again easy to do in LlamaIndex. You simply create a loop. In this case, the loop loops back on itself, but you could go many steps of chaining down before you decided to loop back to some other step. The real power here is obviously combining all of these patterns. You can create arbitrarily complex workflows to handle any combination of circumstances. But right at the beginning, when I was defining an agent, I said it was about the ability to use tools. And so far, we've only discussed that in the abstract. Here is how you actually do that. Tools are just Python functions. That is it. Any function can be a tool. You need to give it a descriptive name and a doc string because that's how the LLM knows what the tool does. Type hints also help the LLM pass parameters correctly to the function. What you do with your tool function is you give it to an agent, literally by passing in an array of functions, along with a system prompt to tell it what to do with the tools. LlamaIndex currently has two built-in agent types which accept tools. One is React agent, which works with every LLM. And the other is function agent, which works with more capable LLMs like OpenAI, Anthropic, and DeepSeek. What this allows you to do is create workflows that are multi-agent systems. You can put as many agents as you need in as many steps as you need, and you can connect them with events. It is simple and it's elegant, and our users like it a lot. In fact, multi-agent systems are such a popular pattern that we created a shortcut to building your own. It's called the agent workflow, and it's built on top of workflows, so you already know how much of it works. You use it by creating as many agents as you need, such as the one shown here, with as many tools as each one needs. This is the same as how we created an agent before, except we've added a name and a description so that the agents can figure out what the other agents are doing. Then here, in technically what is a single line of code, you can instantiate the agent workflow itself. You give it all the agents you created, and you tell it which agent to start with. And you also give it an initial state of the world. Then your agents can take it from there. They will use their tools, and they will pass control back and forth between themselves until they have completed the goal that you gave them. So now you've learned very quickly what workflows and agent workflow are, but that is a lot to take in. Don't worry, we have a step-by-step tutorial about how to build workflows and how to use agent workflow. It's available at this link, which you will also get at the end of the presentation. It should take you about half an hour to get fully up to speed. As we discussed earlier, one of the most powerful tools that you can give an agent or a multi-agent system is RAG. Let's talk about how to actually do that in LlamaIndex. First, let's talk about how to build a RAG pipeline in practice. You ingest your data from wherever it lives, you parse that data into smaller chunks, and you run those chunks through an embedder. You store those chunks in a vector store, and then you use a query to perform semantic search on the chunks in your vector store. You take the chunks you retrieve, and you pass them to the LLM along with your query, and the LLM generates a response to the query based on the data that you gave it. In LlamaIndex, building a RAG pipeline with all of those steps is just 5 lines of code. In the first line, we use LlamaParse to load and parse the data. LlamaParse is optional. We also have other options for parsing locally. Then we embed and store the resulting documents. This is using OpenAI by default, but you can use any other embedding model. Then you turn your index into a query engine, which is what actually does the RAG part. You query it, and then you print your response, and then you're done. Of course, this is very simple RAG. In reality, RAG has trouble answering some kinds of questions like summarization, comparison, and multi-part questions. To address those issues with RAG, you can use the other techniques we discussed earlier. Patterns like routing, orchestrator-worker, and evaluator-optimizer were specifically designed to address these limitations. RAG is a super powerful tool, but you don't use it by itself. You build it into a larger agentic strategy. Why is summarization a problem? Because RAG is designed to select a subset of your data, but summarization requires all of your data. The pattern you can use here to resolve this problem is routing and parallelization. When you see a question about summarization, don't send it to your regular RAG pipeline. Send it to a summarizer that splits up your whole document, summarizes each of the chunks, and aggregates that into a single summary. Ideally, you do that once in advance so that you're not constantly summarizing your document. Comparison tends to fail in RAG because it tries to retrieve chunks about all of the things that you're comparing all at the same time. And it then gets confused about which chunk is which. A parallelization strategy here is obvious. You can ask questions about each thing, and then you aggregate the answers about each thing and get it to answer a single comparison based on the data that you've retrieved. And then multi-part questions fail, as I mentioned earlier, because RAG is good at getting context for one question at a time. So you can solve it by using chaining and or parallelization to split up your question into many simpler questions and answer them separately. What happens next is up to you. We are excited to see what you can build with all of this, and we welcome feedback from the open source community, which means you. You can join our Discord to ask questions of your peers, and also our engineers hang out there all day. So you can always ask them questions. We have extensive documentation that I've personally spent a ton of time writing, so we welcome feedback on that too. I hope this has been a useful introduction to LlamaIndex and what it can do, and also the wider world of agents and retrieval augmented generation. You can follow this link or this QR code to get all of the slides that you saw today, plus all of the links to examples that you might have missed. It's been a pleasure to speak to you, and thank you for your time and attention. Why can't the LLM alone handle all the parallelization at once? You can try giving your LLM multiple parallel questions, but it is bad at that. They are designed to answer one, to do text completion one at a time. So if you give it a whole bunch of questions all at once, a bunch of questions in parallel, it's going to answer them all in one go. And it's not necessarily going to devote all of its thinking time to each question. If you give it each question separately, it's going to do a better job because it's going to have more attention to spend on each question. But that's an excellent question. Is there an advantage that LlamaIndex has over LangGraph? Is it the simplicity in use and the visualization that LlamaIndex brings to the table? That's an excellent question, and I love that you have answered it for me. Yes, those are the two things that we like about LlamaIndex over LangGraph. Specifically, the thing that we think provides a better developer experience is the event-based nature of workflows. The graph in LangGraph is kind of a barrier to doing complex flows. It becomes difficult to do branching and looping and stuff like that, while an event-based pattern is more flexible. So that's why we picked it after initially trying a graph-based approach and not liking the ergonomics of it.